Hello everyone, welcome back to this Applied Remote Sensing Training Part 2 on the application of Earth observations for assessing waterborne disease risk. This is Amita Mehta and we have guest speakers today, Dr. Antar, Jutla and Bailey Magers. They will be talking about using remote sensing based Vibrio predictive intelligence for intervention and mitigation. So that is going to be the topic today from our guest speakers. I will introduce them briefly, but just a few things to note here. Homework, there is one homework assignment and that is posted today on the ARSET website. You can also get it here from the training website and it's due on 10th of April. And a certificate of completion will be awarded to those who have attended both sessions live and complete the homework assignment by 10th of April. Before we start with today's session, here is a brief review of what we saw in part 1. We reviewed common waterborne diseases and pathogens, including diarrhea, cholera, typhoid, polio, hepatitis A, etc. Then we identified environmental parameters relevant for inferring the presence of pathogens in water. And these highlighted parameters here, they are available from Earth observations, either from remote sensing or from Earth system models in which remote sensing data have been assimilated. So we saw that chlorophyll and harmful algal bloom or cyanobacteria and colored dissolved organic matter, these can be detected in water bodies from satellite images. And there are other parameters such as precipitation, runoff, soil moisture. They can be derived from Earth system models as well. Then we introduced satellites, sensors, and Earth system models to obtain the environmental parameters and identified advantages and limitations of satellite remote sensing data. So you might recall that we looked at a number of satellites and sensors flying on them and also talked about Earth system models. These satellites and models, they provide a number of environmental parameters, weather, climate, and hydrology parameters we talked about, and they can be used to infer to presence of pathogens in water. We talked about how these data are advantageous to use over in situ or sample data because they have large scale coverage, they're continuous in space and time, they're regularly gridded, so they can be easily used. We also saw some disadvantages, that they all have different SWOT weights and resolutions. Also, if it's cloudy, then optical satellites cannot see the surface. But overall, combination of satellite data and model data, they can be very useful because of their nature. Then we had a demonstration of 3 web tools for search, visualization, and access of Earth observations. We had Earth Data Search Portal that can help you search any data that you're looking for and then download either single or multiple maps or images, or download in bulk. You can customize spatially and temporally your data, filter variables. You can decide formats in certain cases and download data. We saw NASA Worldview, which provides near real-time data in addition to historical data, and it's very useful for visualization of data without even downloading. And then finally, we had a demonstration of cyan or cyanobacteria assessment network to look at cyanobacteria bloom in lakes in the United States. So before I introduce our speakers today, just a note about asking questions. So you can put your questions in the questions box and we will address them at the end of the webinar. And feel free to enter your questions as we go, and we will try to address all of them. If we cannot, Then we will answer them in the question and answer document, and that will be posted on the training website about a week after the training. So I'm going to introduce our guest speakers for today. First, Dr. Antar Jutla is the director of USGS Florida Water Resources Center and associate professor in the Department of Environmental Engineering Sciences at University of Florida. He received his PhD in Civil and Environmental Engineering in 2011 from Tufts University, majoring in water resources. His primary research areas include water systems, coastal and oceanographic engineering, new infrastructure planning and management, system ecology and ecological engineering. His research interests are in hydrology, remote sensing, public health, water and vector-borne diseases, hydrological modeling. Dr. Jutla has received a number of awards, including Charles S. Falkenberg Award for American Geophysical Union in 2023. He has received NASA Applied Science grants for forecasting cholera outbreaks, and he is an early adopter of NASA PACE mission working on a predictive assessment of clinically active biothreats in coastal and ocean waters using PACE data. Our second speaker today will be Bailey Majors. He is a PhD candidate in environmental engineering from the University of Florida's Engineering School of Sustainable Infrastructure and Environment. He is a member of Dr. Antar Jutla's GeoHealth and Hydrology Laboratory, starting with the lab in January of 2020. His research has primarily focused on making applications with waterborne diseases, particularly pathogenic Vibrio. He has developed a predictive model for cholera that is currently being used in many countries around the world, such as Haiti, Kenya, and Yemen, to help public health officials make informed decisions on mitigation of cholera. Following the success of these initiatives, he has been focusing on developing a similar model for vibriosis cases in the United States. So with that, I invite Dr. Jutla and Bailey Majors to talk about using remote sensing based Vibrio predictive intelligence for intervention and mitigation. So Dr. Jutla, thank you.
Thank you, Amita, for introductions. I'm going to start this training with a brief overview of how Earth observations can be used to determine the risk of waterborne diseases. And we will focus on the use of these Earth observation technologies to understand when, where, and how different waterborne pathogens are likely going to emerge, and then how we can predict those pathogens and their interactions with human population. The two objectives of this training are to recognize how satellite observations are used to predict waterborne diseases, and then appreciate that the satellite observations have capabilities to provide water quality data that we can use with other data sets, including land use, land change, sea surface temperatures, air temperatures, vegetation, coastal ecology, and then basically start to ask questions on prediction of some of these waterborne diseases in human population. The way that this training will work in next few minutes would be that I will give an overview of how waterborne diseases, or what kind of waterborne diseases exist, what is their current threat to the US and to the world. We will go we'll take a deep dive in one of the major pathogen of the world, waterborne pathogen of the world, which is known as the Vibrio cholerae. Vibrio cholerae is responsible for causing cholera outbreaks since early dawn of first century, and we are still trying to figure it out where, when, and how cholera is going to impact human population. Um, After that, we will go with the art of prediction, where we will discuss how we have used satellite data sets to develop models for prediction of these Vibrios. Then we will switch to Bailey, who will introduce a cholera risk model. The reason that we will choose cholera risk model is because we have a lot of data sets, both in situ disease surveillance and epidemiological data sets that was incorporated into a modeling system, and that where we also link these satellite data sets into those models. Finally, we will be looking at the interpretation and understanding of the cholera risk model outputs, because the modeling outputs are a little bit the modeling outputs are not based on the traditional model outputs, where the traditional models basically provide an estimate of how much population is going to be at the risk. Rather, we have devised one of the new methodologies where the risk is based on the geographical location and the availability of water and then water quality. And then we will look into some of the lessons learned from this technology, and then the applications in the Gulf Coast near Florida. So we'll start. So we started our work with Vibrios. Vibrios are it's a kind of a bacteria. The bacteria survives in the brackish waters of the world. Vibrios pose an inherent threat to human population, and then these some so Vibrios are autochthonous to the aquatic environment, meaning that they are going to be present in and around coastal waters, in freshwater systems, given the conditions are appropriate for their growth. So we will take the example of Vibrios and then develop the models and modeling systems for understanding the risk of exposure to human population. Before we begin there, we want to show a little bit on where or how different type of waterborne pathogens are associated with the environmental variability of different parameters. So on this slide, what you are seeing is a summary of key waterborne pathogens which have environmental associations, and the corresponding temperature and salinity ranges based on the literature that is available with us at this moment. So we'll see that there are a host of pathogens that have impacted human populations, which includes Cryptosporidium, E. coli, Giardia, Legionella, Salmonella, Schistosomiasis, Shigella, Vibrio cholerae, Vibrio parahemolyticus, and Vibrio vulnificus. So all of these pathogens, they are waterborne pathogens, and all of them have a different favorable ranges for salinity and temperature. In this presentation, we will be focusing on Vibrios. So we will go with this idea of how Vibrios are impacting coastal populations, and then how we have used Vibrio cholerae as a signature pathogen to understand the risk of disease in human population. In general, um, ocean warming, ocean acidification, precipitation extremes, salinity, ocean oxygenation, and increased nutrient runoff are one of the key variables that impact the prevalence as well as emergence of waterborne pathogens. And then we have seen these factors playing a role in enhanced variability of these pathogens up along the Gulf Coast in the US. So Here you're seeing the impacts of Hurricane Ian, where this devastating hurricane had hit the coastal Florida in September of 2022, and we saw a spike of Vibrio cases, particularly Vibrio vulnificus cases in Florida. Vibrio vulnificus is again a species, is a Vibrio species, different from cholera, but from the same family. Uh, and the characteristics of Vibrio vulnificus infections is that it is characterized as a flesh-eating bacteria, meaning that it infects the human limbs and human skin, and it often leads to amputations, or it often leads to fatalities. And that is and then this is the bacteria that lives and survives in the coastal waters in the Gulf Coast. So we have been tracking, our research group has been tracking these Vibrios all across the world, and we have been focusing on this idea of predictability of global Vibrios in the world, with particular focus in and around Gulf of Mexico. Just last year, after Hurricane Milton, we saw a spike in cases of flesh-eating bacteria, and and then and last year um, it was one of the deadliest outbreaks of these Vibrio vulnificus cases in human population along the coast of Florida in the US. So our idea here is to basically get ahead of this curve, see where these Vibrios live, how these Vibrios survive, what are the optimal conditions, and then basically build a model, a prediction model that will have a certain lead time, so that we can inform human communities, hospital systems, that something is going to happen in near future or not. Vibrios are not a new species. Vibrios are present in the aquatic environment. In this slide, what you are seeing is an annual trend of various Vibrio species that have a potential to impact human population in the US. So so this graph goes from 1990 to all the way to 2019. And as you can see, the number of vibriosis cases in human population is increasing over time. So the cases, although the cases remain low, but there is a strong upward trend in almost all the cases, all the Vibrio cases that impact human population. And on the right-hand side, we see some of the impacts of vibriosis in human population. So these are the typical characteristics of an infection when vibrios infect human population. Um, the These also impact the oysters, and where the consumptions of oysters or seafood is high, the likelihood of exposure to Vibrio species is going to be high in those populations. The next slide shows the presence of these pathogenic Vibrios in the US. On the left-hand side, you'll see the states that have an active coast or a coastline, and then and the composition of the vibriosis cases by species. So if you look in Florida, we have almost all kinds of species that infect human population. And if we go north, the Vibrio parahemolyticus dominates the infection in human populations. On the right-hand side, you're seeing the types of species and the cases that are reported in and around the coastal locations of the US. And this data goes all the way back from 2010 to 2019. One of the notable conditions or one of the notable observations here is that over time, the cases of Vibrios has shifted from south to north, meaning that we are seeing an increase in cases in the northern latitudes as well. We are seeing more and enhanced variability in the type of Vibrio's outbreaks in the southern US. This slide shows a temporal trends of Vibriosis and Vibrio vulnificus in Florida. So, the red, the red in the the red counties basically shows that these are the counties where there is a positive trend or an increase in Vibriosis cases over time in Florida. So as you can see that most of the counties in Florida are experiencing an increase in the cases of vibriosis over time. We are particularly focused on Vibrio vulnificus because Vibrio vulnificus uh, tends to have a more serious health complications than otherwise. So Vibrio vulnificus, like I said before, it often leads to amputations. It often leads to mortality if it is not treated properly over time. So even the Vibrio vulnificus trends in almost all the counties is showing a positive trend over time. The Vibrios in general are associated with sea surface temperature, precipitation extremes, floodings, coastal salinities, organic matter, and chlorophyll, which is used as proxy for phytoplankton and zooplankton. Um, from this one, the sea surface temperature, precipitation, flooding, coastal salinity, organic matter, and chlorophyll, all these variables can be uh, can be can be estimated using data sets from satellite. For example, sea surface temperature is the sea surface temperature data sets is available from the NASA Earth observations from all the way from 1948 to till date. Similarly, like we have a very good estimates on precipitation, coastal salinity, and chlorophyll from satellites. Uh, the prediction of Vibrios is a challenging task. We have started this project using Vibrio cholerae, but we are slowly progressing to include other Vibrio species into our modeling schema. So in this one, what you're seeing is a typical chlorophyll product from PACE. PACE is a new satellite from NASA, which has hyperspectral capabilities, meaning that it has more wavelengths than any other satellite that is measuring coastal ecological conditions. So we are trying to basically use the PACE data sets to understand where, when, and how coastal conditions are going to be conducive for these Vibrios to start impacting human population. We also do verify our model outputs with genomic sequencing of all the samples that we collect in and around the coastal waters, and then relate those observations to the satellite remote sensing data sets. One thing that we must remember is that Vibrios cannot be eradicated from the environment. They are native species to the water and environment, meaning that they will remain viable pathogens in the water system. The best way we could get ahead of Vibrio's infections is to basically develop an understanding of like when and where the population might be at risk of exposure from these pathogens. Therefore, we are going to shift gears here. We're just going to use how we have used satellite sensing to understand the and build models for Vibrio cholerae. Vibrio cholerae is is a Vibrio is from the Vibrio species, but this is the pathogen that basically is responsible for cholera pandemics in the world. Since we have a lot of data sets from for Vibrio cholerae, so we had that opportunity to build that model and understand how the environmental conditions are associated with this pathogen. And then we will see that how we have translated that information to other Vibrio species. And then we are now trying to build those models for Gulf Coast in the US. So from here on, Bailey Majors will basically take it over and tell us that how we have built these modeling systems and then where we are in terms of the predictability of this disease in human populations. Bailey?
Okay, thank you, Dr. Jutla, for that great overview of kind of the issues surrounding the United States with vibriosis. So a lot of you were probably not familiar with vibriosis before, but thankfully you are now, and the kind of dangers that that presents. Some of you are probably actually more familiar with cholera. It is probably one of the largest and most reported waterborne diseases globally. So it impacts about 50 countries as of 2023, with about 700,000 cases reported and about 4,300 deaths reported. Those numbers are actually probably much higher, as the reporting of cholera, especially in more developing countries, is much lower than it should be, which is mostly noted by the higher case fatality rates. So cholera, typically, we would expect in literature to be about 1% of cases to be fatal. But in countries that are reporting case fatality rates of 3-4%, that means that there's a pretty high chance that those countries are underreporting it. So the actual situation is probably much more dire than the 700,000 cases listed here. And kind of the alarming thing about cholera is that it only takes hours for a infection of cholera to be fatal if it is untreated. And one of our main goals with studying cholera and developing cholera prediction awareness is to help basically distribute supplies and provide awareness of where cholera is most likely to be present, so that these cases can be treated appropriately. So the causative agent of cholera is Vibrio cholerae. And as we've talked a lot about Vibrios before, I wanted to give you some more context specifically to Vibrio cholerae. So the main way that cholera is, the infection is caused is by consumption of contaminated drinking water containing this Vibrio. Specifically, it is found in riverine, estuarine, and coastal environments, as well as certain freshwater ecosystems, depending on the salinity content of the water. So Vibrio cholerae typically is found in waters of salinity profiles about 5 to 25 parts per thousand is considered like the optimal range for them, with estuarine salinities of around 15 parts per thousand being much more optimal. It is also an ecologically significant bacterium, as all Vibrio species are, meaning that it cannot be eradicated from the environment. Therefore, the infections of cholera will continue if treatment solutions are not provided and sanitation infrastructure is not robust in our infrastructure. So cholera is generally caused by consuming a large enough dose of Vibrio cholerae to cause an infection. This is important because Vibrio cholerae, as it is generally ubiquitous in the environment, there are certain environmental conditions that cause it to be more abundant in the environment than at other times, and it makes it an interesting pathogen to study for this reason. So the timeline for Vibrio cholerae and cholera research really spans back about over 60 years, ever since kind of the first microbiological studies were being done on the presence of Vibrio species and the associated environmental parameters with their presence. So things like temperature, precipitation, and salinity were some of the first things to be actually studied, and establishing kind of the microbiological principles of when it is found, where it is not found. And since then, getting into the characterization of serotypes and things like that for Vibrio cholerae, as genomic sequencing and PCR and things like that were starting to, the technological innovations were becoming more prevalent. Then we get into the advances in geosciences, where satellites and satellite data started to first be used to link environmental conditions with cholera outbreaks. Some of the first things that were linked to cholera outbreaks were things like sea surface temperature, sea surface height, in areas where previously we have not been able to study because we don't have that availability of data, but Earth observations gave us that opportunity to have those studies. And since then, in the last decade or so, we've spent a lot of time in our group with the University of Maryland developing this 4-week predictive system for cholera, especially in endemic and epidemic countries. And now we are moving towards real-time prediction of cholera, where we have developed this model. And I will be able to tell you a bit more about the kind of underlying science and the ways that we got there. So I'm going to talk a little bit about the art of prediction and why it is that we're very interested in predicting the presence of cholera, not just obviously for the humanitarian benefit, but what are the larger impacts that we can do by studying cholera, and how do we, what does prediction really mean? What is our main goals? What are we trying to accomplish? So for most outbreaks of a infectious disease, it is done in response to the disease being prevalent, and typically the public health officials or the local government decides that the situation has gotten dire enough. We need to actually intervene now and distribute supplies because people are dying and people are getting sick. Typically, what that looks like is in scenario B, we have a peak of an outbreak of a disease. Let's say in this case cholera. And the intervention point is at the peak of the disease, and there's only a relatively small impact made because we are intervening at a point where the situation is already super dire. Our goal is to have an epidemic curve that looks more like scenario A, where we intervene before the actual outbreak is at its worst, through prediction of when it will actually the outbreaks will happen and when they will be at their worst. Hopefully to reduce the actual volume of the epidemic curve and the number of people that are infected. So as I was saying, one of the first studies that looked at using remote sensing for cholera was in the early 2000s, and looking at sea surface temperature, sea surface height in for cholera cases in I believe in the Indus River Basin. So this was one of the first studies that was ever done using remote sensing data and cholera. And a lot of the work for remote sensing for the use of waterborne diseases really started with this paper establishing the correlation between a combination of sea surface temperature and sea surface height, where warm waters will inundate the inland areas, allowing the proliferation of cholera in the water bodies, where people will go get their drinking water or will wash their clothes and things like that, where the interaction between human and pathogen is much more likely. And since then, a lot more work has been done in the similar area. So one of the first studies that kind of Dr. Jutla's group was involved in is looking at the odds of cholera in the Indus River Basin using both average and below average temperatures and average and below average rainfall. So what we see from these graphs here is that the odds of cholera are generally much higher when the temperatures and the precipitation are above the climatological average for that region. And that was true for pretty much all of the different regions within the Indus River Basin that we were looking at. And from this, we have kind of developed a cholera hypothesis where the environmental sensitivity of cholera is related to temperatures, precipitation, and water security. So I'll go ahead and walk through exactly what the details of this are. So the first component of this hypothesis is above average temperatures. As I was saying, it increases the odds of cholera presence and outbreaks. Generally, the thinking is that 8 weeks before a reported outbreak, there has been there has been recorded higher than average temperatures, which allow the bacteria to proliferate in the environment, as the increased temperatures are more favorable for the bacterial growth. We use data sources for temperature, including MERIT-2, even the NOAA satellites as well, NCEP, or even Met Office data sets for the temperature data. The next kind of condition that is important for cholera to be present in our research findings is heavy precipitation. So higher than average precipitation for the region allows that flooding of the water infrastructure or the proliferation. So once the bacteria has proliferated in the environment due to the high temperatures, the flooding allows it to kind of the water sources that normally would not be contaminated have a higher chance of being contaminated due to flooding, getting into areas where people actually interact with their water sources more often, and it increases that chance that people will actually have an interaction with the pathogen. Again, our data sources for precipitation have generally been the GPM data sets, as well as Met Office. But finally, the last component that's really necessary for there to be a high risk of cholera is water insecurity. So very often in, let's say, the US, we have conditions where warm temperatures and heavy precipitation are present, but we obviously do not have outbreaks of cholera. And the main reason for that is that we have robust water and sanitation infrastructure, where the treatment processes allow us to have eliminated this pathogen from our water sources that we interact with daily. But in places where this is not the case, whether it's due to the just lack of infrastructure or there is a ongoing conflict, people are displaced, or any number of natural disasters. So even in the US, when we had things like Hurricane Katrina, there were actually reported cases of cholera because the massive increase in temperatures and precipitation, as well as the destruction of water infrastructure there, kind of created the conditions for this outbreak. And we get those data sets typically from places like WHO, UNICEF, and a whole bunch of other places, typically local governments as well, if they're willing to share those with us. And all of these conditions really lead us to the high risk of cholera, which we can output at a pixel scale to identify high risk areas. So this is kind of an overview of the actual model that we have, which we have named the UF weighted raster algorithm. What it does is it incorporates all of these different factors, both socioeconomic and environmental, to output a risk map that shows which areas are at low risk to high risk in a certain country or a certain region, depending on what we want to look at. So the environmental module, which is kind of the underlying hypothesis that I just showed you, is typically included of air temperatures and precipitation, but we can also include a number of socioeconomic factors, including population density, income, displacement, age, data on natural disasters, anthropogenic disasters, civil status, or any kind of like conflict going on in the region. And then perhaps the most important one, if we're looking at certain areas of countries that might be a little bit different in terms of the infrastructure, is the WASH module. So if we have information on access to safe drinking water, access to safe sanitation, those will actually improve model results the most. In addition, obviously, with the environmental module, to try and estimate which areas actually have the highest risk of an outbreak. So these are the data products that we currently use in our cholera model. So we have, for historic precipitation data, we typically use the TRIM data sets. For recent precipitation data, we use GPM iMerge data sets. For both historic and recent temperature data, we use the MERIT-2 data sets. We've also started to incorporate drought as a component, which I'll talk about a little bit later. We use SPEI data for the drought index from ERA 5 reanalysis. And finally, for population data, we use ORNL Landscan products. So all these sources are available publicly online for free, where anyone can go and download them if they wish to view the same data sets. And now I'm going to talk a little bit more about how we actually incorporate those data sets into our cholera risk model and how the model actually works. So our first kind of look at using this cholera risk model, one of the first projects that we did was after a natural disaster in Nepal, where there was a huge earthquake, especially in the Kathmandu region, which is the capital of Nepal. This outbreak of cholera resulted from a lot of the infrastructure damage that was done to the water and sanitation infrastructure there. Interestingly, the main goal of this project was we identified areas of high cholera risk where the conditions were right for an outbreak. But by being proactive and communicating these responses with local communities, we were able to basically identify areas where wash infrastructure should be strengthened, and the strengthening of that infrastructure actually decreased the risk of cholera in those areas and decreased the number of cases that were being reported during this time. So this is one of the first applications of this model, again, using that hypothesis of higher than average temperatures, higher than average rainfall, and including the wash component into this, where the resilient wash infrastructure was able to prevent a much more severe outbreak from the natural disaster. And this is kind of another look at Nepal. Before that earthquake, we also looked at just using the precipitation and temperature anomalies to identify high-risk areas. And what we found is that the accuracy of our predictions pretty much lined up with where the cases were being reported in that region. More recently, cholera is typically thought to be endemic to places like Africa, the Middle East, and those kind of areas, and even in parts of Asia. But for Haiti, the cholera outbreaks that have been going on there have been much more recent. So in 2017, we did this study looking at cholera reported after a outbreak, or after Hurricane Matthew went through the country. Down on the bottom left here, you can see the identified areas of hurricane severity on these red dots, as well as the high risk of cholera, which is in the red. And obviously with the things like hurricanes, there's a much greater amount of precipitation and rainfall in the area. And this actually led to us identifying areas that would have the higher risk of cholera, which is where the cases were actually reported. And we've continued to monitor places like Haiti for these kind of disasters, just in case, especially because Haiti is very hurricane prone. There's a lot of hurricanes that go through Haiti, and they're currently experiencing a cholera outbreak. So we continue to monitor the region as well. But just because there is more rain, so in the event of a hurricane, typhoon, those kind of big natural disasters that present a lot of flooding and rainfall, it does not necessarily mean that there will always be cholera. So another key component of that, of course, is the temperature component. So one example is in India and Bangladesh. There was a huge flooding scenario occurring, I believe, in 2019, 2020, where we had a lot of reports of flooding, and there was a big outcry that there was going to be a cholera outbreak due to the flooding in the region. But our model suggested that this risk was low because the temperatures of the region were below average. In fact, they were much below average for that time of year. So even though there was a big clamoring that there was going to be this outbreak, we kind of stood on our hypothesis and said that there wouldn't be. And what we actually found was that there ended up not being a cholera outbreak there. That's providing more evidence that temperatures are a very vital component of this. Perhaps our most successful story of cholera prediction is in Yemen. So this is a recently published article showing how we've used our cholera model for prediction at a county level scale in Yemen over, I believe, a 3-year period. So Yemen had one of the worst cholera outbreaks pretty much in this century. It's possible that there might be a worse one to date now, but as of about 2017, at that time, it was the worst reported cholera outbreak of this century. And the amount of data that we were actually able to get from this helped us it provided us with a unique opportunity, basically, to study a long-term scale of how effective our model would be So we had weekly cholera data sets at a county scale for about 3 years that we were able to basically run our model for the same time period each week, compare the high risk areas and the low risk areas of the model to the actual cases reported. So for this model, we ended up being 70% accurate in the regions that we studied in Yemen. And one thing that we also noticed is that we were much better at identifying the false positives than the false negatives. So basically what that means is that when we're thinking about prediction scenarios, it's much more important for us to have said that there's a risk, and then if nothing happens, that it's not ideal, but it's okay. You know, those things happen. It's much more important for that to happen than for us to say that there will not be a risk and an outbreak does happen. So in this case, it's much less likely for us to identify those scenarios where we say nothing will happen and something does happen. So that's another strength of the model. We've also done validation for this model on more of an outbreak scale than the case-by-case scale. Kind of the problem with one of the problems with trying to do model validation for cholera is that the data sets are often very lacking. So like I said, Yemen is a unique opportunity that we had these continuous weekly data sets for 3 straight years at a county scale. It is very rare for us to get data like that to do a validation study. But we are looking to, and working with other regions to hopefully try and do separate validation sets or testing so that we can get more information about how our model performs. Now, one of the ways that we want to, or that we've looked to improve our model is looking at incorporating drought as a component. So we have sort of observed a few regional anomalies with our hypothesis. Specifically in 2022, we looked at an outbreak in Ethiopia that did not fall under the conditions of our previous hypothesis, where at the time there was not higher than average rainfall, there was no evidence of flooding, but there was a drought. In fact, one of the worst droughts that the region had ever experienced at the time of the cholera outbreak. Once we looked more into this region and other regions like Ethiopia, we noticed that there was a pattern of places that were undergoing a drought and had, again, that higher than climatological average temperature in the 8 weeks previous to the outbreak. But this time in combination with a lower than average precipitation for the previous 4 weeks when that drought was present, that led to the higher risk of cholera outbreaks if the wash infrastructure was unavailable or damaged. Basically, the reason for that is that the water insecurity, or at least what we believe is going on, is that the water insecurity at the time of the outbreak is what's causing people to interact more with the Vibrios in the water, whether that be because people have less water availability and they have to seek out other water sources, or the actual concentration of the pathogen in the water sources is higher because the water sources are drying up and the volume is smaller. It could be for either reason. But still, an essential component of that is still under normal conditions where there is no drought. Our original hypothesis, of course, still holds. And kind of the idea of this is that either extreme is important to consider, not just for cholera, but for other waterborne diseases. Drought has been identified as a indicator as well. And it is something that we've incorporated in our models going forward. In fact, what we found is that cholera outbreaks are about 3 times more likely during a drought. In specifically drought-prone regions of Africa, when we combine this idea of drought with our hypothesis, we actually found that even in these most drought-prone regions, it's about 3.5 times more likely that a cholera outbreak will occur during these extreme climate events. So we've incorporated drought indexes into our model and this new combined extreme hypothesis into our model. Specifically in Ethiopia is where we've seen the most success. Unfortunately, we don't really have the epidemiological data sets to do validation like we did in Yemen. Kind of like I said, those are really hard to come by. But based on the reports that we've had with our local partners and people that are in country, we've been able to more successfully identify regions of high risk than we were before, and able to capture the outbreaks that perhaps we were missing in the past. So this has been generally a success story, at least for Ethiopia, and we're looking to test it in other regions as well and see what kind of results we get there. So kind of the last part of this is we have this model. We were able to identify high and low risk regions, but what exactly does risk mean? And how do we understand what to do in high risk or low risk scenarios? So one of the most important things that we consider when we're interpreting our risk maps is this idea of threat level, which we would consider the risk score, which is what we call the actual risk values from the model, plus the rising or decreasing values of those over time. So this graph on the left, if we have been seeing an increase in risk scores over the last several weeks, this is a kind of an alarm for us that things should be moving towards intervention. We don't want to see a case where we wait too long as risk has been increasing for several weeks. We don't want to wait too long where the outbreak has already happened before we say anything. This is where we might want to contact our partners and start open a dialogue with them basically and say hey, what's going on in the country? Is anyone reporting these diarrheal cases? Is anything going on right now? Just so that we can get ahead of what's coming. However, even in scenarios where, say, the risk scores are high, but they've been decreasing the last several weeks, this might, still be an area where we're communicating with our partners and saying, hey, the risk scores are still high, but we've noticed that the situation might be easing. And so maybe the interventions might not be as urgent at this time, especially if we see continued decrease over the next several weeks. To the point where, the cholera risk really isn't there anymore. So this idea of threat level is also taking into account how the last few weeks have been behaving. Are temperatures increasing? Is rainfall increasing, et cetera? And then another key part of this is defining risk thresholds. So from the studies that we've done in Yemen and in other countries, we've identified these thresholds as of high, low, and medium as the optimal values for our model. So anything in our model computes risk on a scale of 0 to 1, with anything below 0.3 being low risk, anything between 0.5 to 0.3 being medium risk, and anything above 0.5 as being high risk. High risk basically means that there is a high chance of populations that have the insufficient wash infrastructure interacting with contaminated water sources that contain the bacterium, and that regions will have cases of cholera generally greater than the spatial average of cases for that region. Whereas medium risk is that there's still a chance that that the human populations there will, with the insufficient wash infrastructure, might interact with Vibrio cholerae, but it is a little bit less likely. And we will need to monitor that region over the next 4 weeks or so to kind of see what the situation is. Is the risk changing? Is it increasing or decreasing? Kind of, like I said, with the threat level idea. So if we have medium risk, but that risk has been increasing over the last 4 weeks or so, we might start to want to think about doing actual interventions at that point, or at least preparing to do something should the risk go above that threshold for high risk. But medium risk does imply that the region is 1 standard deviation below the spatial average of cholera cases for that area. Finally, we have low risk, where essentially there's no or very low risk of cholera. And generally, if an area is in low risk, we would expect essentially 0 cases of cholera to be reported for that region during that time. So kind of just some disclaimers about what the model can be used for. Risk cannot be converted to a number of cases. So it is based entirely on the actual how cholera is reported in that region. So like I said, above the average for that region within 1 standard deviation are kind of the measures of how we interpret risk. But we can't say, oh, the risk is 0.9. That equates to 500 cases of cholera. That's not how it works. So it's not an epidemiological say compartmental model, so an SIR model or something like that that converts directly to transmission risk. It's not quite a model like that, so we can't convert to number of cases. But another thing to kind of take note of is that the model results are good for the next 4 weeks, but week-to-week variation should be taken with caution. So there are some weeks where even though our forecast is generally good for 4 weeks, the risk might go up for 1 week, but the next week go back down. So we should be very cautious when we interpret risk just on one event. We should take a few weeks of risk into account before making any kind of decisions. So what we do for our local partners and for any of our international partners is that we generate these situation awareness reports if they are requested. So for new regions, it typically takes us about 10 days to generate one of these reports. And for existing regions, it's about 3 to 5 days. And we'll send them weekly to any countries or interested parties for the kind of cholera period that they're wanting to look at, depending on if they want us to continue sending these reports. We also have an email here for anyone that's interested and who wants to, kind of contact us and talk about maybe seeing a report for their region. But on the right, this is kind of what they look like, where we identify the region, the forecast period, what the level of threat is. We have a what to do, which is like an activity for how they should address the situation. And these reports will contain the prediction maps as well as any, kind of advice we have on the actual situation going on there. So speaking more on the activities that are included in the situation awareness reports, this is how we define what countries should be doing in high, medium, and low risk scenarios. In the high risk scenarios, which are the most important ones, the main things are that the wash infrastructure and education about how to properly, sanitize and proper hygiene, those kind of things are most important. And then if there's the possibility of collecting water samples to identify hotspots for cholera presence, then that would be ideal. But unfortunately, a lot of these regions don't have the supplies to do that. So this is more of like a best case scenario if we're able to do that. And then obviously medical intervention, getting access to doctors and hospitals should be prioritized, as well as distributing any medical supplies to the more cholera prone regions should be prioritized as well. In medium risk scenarios, the kind of general guidance is that, provide the wash and education, given that the risk does exist, but the fact that it's not an alarming level says that there shouldn't be extreme measures being taken at this point. We also would recommend doing microbiological analysis if possible. But again, this depends on the resources of the country. And finally, medical stockpiles should be made for a possible outbreak, especially if the risk has been increasing week over week, so that they're ready for a possible outbreak if it does happen. And finally, in cases of low risk, we would just recommend that they sustain the current level of wash infrastructure that they have and obviously continue to educate the community on the potential risk of cholera, particularly if it's an endemic area where it is a seasonal presence and they might have an outbreak in the next few months or so. And then we are also going to talk about how the lessons that we've learned from cholera can kind of be applied to future applications in the Eastern United States with vibriosis and with other Vibrio species. So the main place that we've been keeping track of kind of our lessons learned from cholera is on the Vibrio Prediction Hub. So the Vibrio Prediction Hub is where we post all of our cholera risk maps. And we also have some information on there as well with the other Vibrios that we've been studying, not just in the United States, but around the world. So if you're kind of interested to learn more about the research that we've done on cholera and what our risk maps actually look like, you can visit this website. But I'm going to turn it back over to Dr. Jutla to kind of close us out and talk more about how we can learn from this cholera risk model and apply it to Vibrios in the United States.
Thank you, Bailey, for going through the prediction of cholera system and that how we have used that one to inform different communities, countries in the world. So on an ending notes, we are trying to expand what we have learned from cholera to the Vibrio's problem in the US. So here on this slide, what you're seeing is the is the probabilistic model that is developed by NOAA for Vibrio vulnificus in Chesapeake Bay. This is a regressive model which basically provides the likelihood of counts of Vibrio vulnificus in Chesapeake Bay. And it also gives an information on what is the likelihood risk of these Vibrios, just Vibrio vulnificus, in the entire bay. Now, this is a heavily data-intensive model that uses a part of satellite data sets, but mostly it takes advantage of the in situ data sets more than the satellite data sets. We do have a good coverage of sea surface temperature and salinity, salinity in Chesapeake Bay. So we are working with our stakeholders and our partners to build a model for these Vibrios in and around Chesapeake Bay. And we are very confident that that the PACE products are likely going to be helpful for us to build future models for Vibrios all along the eastern coast of the U.S. So in this one, you are seeing the sea surface temperature and the plankton activity that is provided by PACE satellite sensors. So as more and more data sets are available at higher spatial as well as spectral resolution, we expect that the models will improve, and then we will be able to produce a near real-time predictive capabilities of exposure of Vibrios to human communities all along the eastern coast. Um, so ending this training presentation, we have successfully developed a prediction model using a long-term data sets that were collected starting 1960s on Vibrio cholerae, and then link it with the environmental variables that were measured and then computed using NASA's satellite data sets. So as the new technologies as the new satellite sensors become available, we will be able to develop the modeling capabilities for all waterborne pathogens, as long as we can define the association of those Vibrios with the environmental and ecological factors. Um, the models that we have built for cholera have provided us with an impetus to basically build those similar technologies for the coastal U.S., especially in the Gulf area, which is not only which is critical for the entire for all the states that borders the Gulf. This is especially true because the Gulf regions harbor a massive fish and aquaculture industry, and it also is a tourism place, and therefore the predictability of Vibrios for operation of beaches as well as the recreational activities will be enhanced if we know that where and when the exposure risks of these Vibrios is likely going to be high in human populations. Satellites provide us with the opportunity to think about interventions in a very different way. So it means that we so right now, the decisions are made, especially the public health decisions are made more on a reactive terms. Reactive terms means that we let things start and then basically start to make the decisions. We want to change that paradigm to anticipatory decision-making systems, which means that satellites will be able to tell us what is the likelihood of presence of pathogens in the water systems that will allow us to build an anticipatory decision-making framework so that we can proactively inform public to make decisions on whether to interact with the water or not, or what is likely going to be the best scenario in which we could limit the exposure pathways of these waterborne pathogens to human communities. we're going to end this training with this satellite with this slide, which shows the satellites that have been launched by NASA, NOAA, and USGS, all the way from Landsat 7 to the planned missions, which includes the Landsat Next missions. So our studies started from Landsat 7, where we use the land use, land change type of activities for understanding where the population density and where the population is moving. We have used multiple satellite systems over years to improve our algorithms. And right now we are very excited to see what PACE is going to offer us in terms of both ocean colors as well as the temperatures and then the spectral wavelengths. With this, we'll stop and back to you, Amita.
Thank you so much, Antar and Bailey, for your presentations. It was really very informative how you combine satellite data and in situ data to come up with cholera prediction model. And this brings us to the end of this training and the conclusion of training. We want to summarize what we learned. So, as you remember, in part 1, we started reviewing common waterborne diseases such as diarrhea, typhoid, cholera, E. coli, Giardia, hepatitis, and polio. They are spread by either virus or bacteria, any pathogens. They're not always directly observed in satellite data, but there are environmental factors that can help in inferring to the presence of waterborne pathogens, which can help us in predicting waterborne diseases. And parameters listed here: water temperature, precipitation and flooding, nutrient and chemicals from agricultural and industrial runoff. So that includes land cover and soil moisture and runoff that controls nutrients and chemical going into water bodies, then chlorophyll and harmful algal blooms, dissolved organic matter, salinity, and solar radiation. And then we looked at some of these parameters, which are commonly used for inferring to waterborne pathogens for common waterborne diseases we talked about. And we talked about these number of satellites. They're optical satellites which can provide imagery and provide land surface and water surface temperature, provide precipitation and land cover products, flooding. We saw atmospheric models such as land data assimilation systems and modern era retrospective reanalysis product like MERA2. They provide products which are not directly observable, such as runoff. And we had a review of web tools to search, access, and visualize Earth observation data that we talked about. We looked at Earth data search, which helps in searching for any data set that you are interested in and guides you to where those data are, and you can download those by spatial and temporal subsetting. Worldview also allows visualization, and you can look at multiple layers at the same time. So we had a demonstration of that. And finally, we looked at cyan, which has capability to look at cyanobacteria concentration in the lakes in the United States based on Sentinel-3 OG data. So this was what we did in part 1. And today then, we recognize the use of Earth observations in Vibrio cholera prediction model. We saw that how this model is developed using satellite data and from NASA Earth observations. We also saw cholera prediction in Nepal, Haiti, and Yemen, some examples. And as they mentioned, there is Vibrio Prediction Hub and Cholera Dashboard that links are available here that you can check them out for more information. So in summary, we saw several advantages and limitations of Earth observations. For example, a wide variety of open source and cost-free environmental data are available. Global, consistent spatial and temporal coverage, and their length is more than 10 to 20 years, depending on which satellite or model you are using. There are web tools available for data search, access, and visualization. Then different data sources they have varying spatial and temporal resolutions. So this is not exactly a limitation, but what that requires is that you have to know about the data sets, their characteristics. You want to use models or a satellite data. So a little bit of information is required here. There is learning there. Then there are data gaps because of two reasons. One is when satellite go over, their swaths are not continuous, and so in between swath, there may be data gap. Similarly, if they're optical images, then in the presence of cloud, they won't be able to retrieve data, and there would be data gaps because of that. So when we have to deal with that. Also, today we saw that in situ water sample data and disease incidence data are necessary for the development of disease prediction models and their validation. So, in what in situ data are obviously very important in development of model. Both prolonged wet and dry conditions impact interactions of humans with pathogens. So this is interesting because when there are droughts going on, there is water insecurity, and then there is unsafe wash conditions, maybe not enough water to wash your hands or use better wash conditions. If there is flooding going on, then because of runoff, there will be contamination in drinking water sources, and then consumption of that contaminated water can put humans in touch with pathogens, and both these conditions can lead to waterborne disease outbreak. We also saw today that increasing risk of vibriosis is there along the southern and eastern coast of US. And with that, there's some note for homework. Homework is posted today on the training webpage, and you will answer the questions via Google Forms, and the homework is due by 10th of April. And those of you who attended both the sessions and complete the homework assignment by 10th of April will receive a certificate of completion via email approximately 2 months after the course is complete. And here's the contact information for our speakers today. And you can always contact ARSET. We want to thank our speakers once again for a very informative webinar today. And we want to thank our coordinator, Natasha Johnson-Griffin, our editor, Susan Monty and Jonathan O'Brien, and our ARSET coordinators, Brock Blevin, Sarah Cutshell, and Selwyn Hudson-Odoy. This is our website address, and ARSET also has a presence on social media if you want to check it out. And the YouTube has training videos. These are our sister capacity building programs, and you can visit those websites as well. So with that, we thank you all for attending this training, and we'll go to the question and answer session now. Thank you. We'll move to question and answer session. Thank you everyone for attending this entire webinar series, 2 parts. Today is the concluding part, and we'll go through questions one by one. We have Bailey here answering these questions. Question 1, is it correct that the Vibrio outbreaks are mainly close to the coastal areas? Therefore, freshwater systems near the coast are more likely to have these Vibrio than the deeper mainland?
Yes, this is a good question. So typically, yes, the Vibrio infections are going to be near coastal areas. Vibrio species are typically found in brackish waters or estuaries. They can also be found in seawater, typically with high temperatures and those with sufficient microbiological communities to support their growth. But most often, their preferred salinity ranges are from about, I believe, like 10 to 20 parts per thousand, which is a bit higher than fresh water is typically reported at, and a bit lower than seawater is typically reported at. So there's two modes of infection for Vibrio species for vibriosis. The first is direct contact of a wound with water containing the bacteria. And that's where you'll see those coastal infections most likely. It's those direct contact infections. The other mode of infection is through consumption of raw or undercooked seafood that contain the contaminated bacteria. So mostly things like oysters, like raw oysters, people order a lot at restaurants. Those carry some risk with them. And this can pretty much happen anywhere, especially given like global trade is, at the height that it's been in history, especially for seafood consumption. But generally, we still see most cases in coastal communities, probably because there's a bit more awareness about what the infections are, how they present, and also probably somewhat contributed by dietary and cultural preferences, more likely to consume seafood near coastal communities. It's also worth noting that the seafood, like foodborne consumption infections, are often not as severe as the non-foodborne, like direct contact with wound infections. So sometimes those foodborne infections can be underreported, and sometimes that can, inform us a little bit about, it's more of like a barrier to us kind of understanding the distribution of these infections, but it's something that we have to work with.
Thank you, Bailey. The next question is sanitation ranked?
So when we input wash infrastructure data into the model, it's typically something that is given to us in like a non-disclosure kind of agreement with the national partners that we're working with, or we send them a map that has just environmental risk and they input the wash infrastructure data themselves. Those are typically considered like sensitive data sets. So they're not shared with us due to like threats of like terrorist attacks and things like that. They don't want people to know exactly where their most vulnerable infrastructure is. And so in a country, those regions can vary quite significantly. And there are some like independent sources that try and rank countries based on the quality of their water and sanitation infrastructure. But typically it's like a bit of a complex process. There are some resources there to kind of give you an idea of like general water sanitation infrastructure globally. So hopefully those could be of use.
Question 3 is the model you generated a raster-based model, and is it available for other researchers to use?
Yeah, so this is a raster-based model. All of our outputs are raster-based. Typically, we average things though over like a county scale or like a regional scale, because most policymakers don't really care about like what's happening on 1 kilometer by 1 kilometer basis. They want to know what's happening in their county or their district, so that they can make like overarching policy decisions. But the main output is raster based, and the only thing is we can't share the actual like model toolkit with you, as it's patent pending right now. So we're unable to share that. But it very much is something that is not particularly difficult to make. It's something that we made it using GRS software, and I'll actually talk about that a little bit more later on. There's another question about it.
Question 4, is there such a thing as a legal threshold for these risk maps?
So we don't really have like, when we define high, medium, and low risk, we don't have a necessary threshold that we feel like we have to stick to. We gave, I believe in the presentation, we give some ranges of what we use currently, but those are just general guidelines. Some regions are different than others. And basically what that comes down to is some people respond to the environment differently than others. Some people are more used to hot temperatures than others. Some people are used to dealing with excess flooding more than others, or drought more than others. And so we kind of have to look at things on a case-by-case basis. So if we see that one country our model's not performing as well. Maybe we're predicting high risk consistently, but there's like very low cases of cholera or outbreaks aren't happening. Maybe we need to consider adjusting the thresholds, or maybe outbreaks are occurring even though we have only like medium risk. So it's something that we don't want to stick to strictly on the threshold distinguishing. And it's something that's we've tried and tested with several regions, and this is the numbers that we have, but things can always change based on new information.
The next question is, which collaboration institutions are you working with in Malawi?
So I know that our main collaborator in the US is University of Maryland. They're the ones that are handling the microbiology part of it. They do a lot of the sampling work and the genomic sequencing. If Dr. Jutla is on the call right now, I'm not sure if he is, he would be able to tell you more about the exact international and national partners we have on that. But typically we work in general with OCHA. We worked with FCDO in the past, USAID, these kind of organizations to get us. Typically what happens is they get us in touch with the contacts in country and they'll facilitate that dialogue. So it's not typically something where people in the country reach out directly to us. It's through some other, international, national organization that we build that collaboration with.
Question 6. South Sudan is a prone area for cholera outbreak in some of the states. Do you have any information for South Sudan in particular that can help to predict the risk and mitigate the impact?
So we're actually looking at South Sudan right now. Particularly what we're looking at is what happened late this past year, what the environmental conditions were leading up to that outbreak. And we'll hopefully have something put together where we can submit an article on that and kind of get a overview of what happened in that situation environmentally. Basically, what we have seen preliminary results kind of show that drought was a significant factor in disease emergence up along the north part of the South Sudan border. They were experiencing one of the worst droughts I think that they've ever had in that region. Which likely contributed to the water scarcity there and eventually the disease emergence, especially with the temperatures, late in the summer being quite significant to support the life of the bacteria there. But the worst that we saw of the outbreak, I believe, was in December of this past year, in a completely different region, but when rainfall was very high in that region, contributing to a much larger outbreak than earlier in the year. I don't have as much information on what is going on at the moment. I believe that cases are generally down from when they were in December, but I would have to get back to you on that to kind of do like an assessment of what the situation is right now.
Thank you, Bailey. Question 7. What are the wash issues? Is there any use to offer infrastructure under X circumstances?
Yeah, so of course, we're always going to advocate for strengthening the water sanitation hygiene infrastructure because not only will that help with the mitigation of cholera by providing people clean water, clean access to sanitation, it'll prevent the spread of other foodborne pathogens, other waterborne pathogens in the water and wastewater supplies. However, obviously the reality of the situation is these resources can't be allocated year round and they can't always be available for everyone all over the world. And so what we typically recommend in our reports is that there are certain times when the risk is high, that supply should be distributed more thoroughly. Obviously one of the main supply distributions would be chlorination tablets for actual clean water. But we also recommend things like oral cholera vaccines, which are harder to come by, but are an option for sure if we have, people from, UNICEF and those kind of organizations have a lot more access to those materials than we do. But it's something we would recommend. So it's really just about trying to identify times when cholera risk is highest. That's when we want to see the wash infrastructure strengthen the most. But we know that that's not always something that's feasible, unfortunately.
Next question is, I'm a Python developer and working with machine learning. Which technologies you use to develop the UFWRA model?
This is a good question. So as I started talking about a little bit earlier, our model is actually quite a simple model. There's not a lot of heavy computational work in it, and it was developed almost exclusively using ArcGIS software and ArcGIS toolboxes to compute the raster files for the model output. So while Python was not used in the actual like creation of the model, we have implemented Python to automate the process for like data extraction, data processing, and computation. And using like the built-in like ArcPython software to automate the process in GIS as well, get those raster files easily. And we're working towards building a cholera decision support system that integrates all this into something that's really easy to use for users, where we could send it as a software to another country, have them input a location, either be a country or a region of their country and a date, and it will download all the data that they need and run the model for them without them having to worry about the exact workings of the model. Like I said, it's like a patent pending model, so I can't tell you too much about how exactly it works, but that's the main idea.
The next question is there some relationship between cholera outbreak and heavy metal pollution in water, perhaps when analyzing mining operations and their environmental impact?
So this is a good question. And there's actually a couple things I want to talk about. So first of all, generally Vibrio cholerae is a very resistant bacteria. It's very resistant to like low oxygen levels. It can be, it's a facultative aerobe, meaning that it can sometimes survive without oxygen. And it also is able to survive in waters with heavy metal pollution. As far as I'm aware, there's no contribution of metals to the bacteria's survival, but there is a possibility that, so one thing that we've learned from studying PFAS, which is more of a plastic contaminant, but the idea here is that PFAS acts as a surface for biofilms, where Vibrios could potentially attach themselves to. We don't have really that kind of data yet to show that physically, but it's a theory that many people have been exploring. And I would say that, I'm not an expert on this kind in environmental contaminants on this kind of level, but I don't see a reason why we couldn't see something similar with heavy metal pollution, where if there's a high concentration of heavy metals in the water, we have these biofilms forming, where Vibrio cholerae presence could be more active. Generally, heavy metal pollution is also associated with water quality, which would indicate more bacterial presence. It's an interesting question. Definitely a good area for future research.
Thank you. It is interesting. Question 10 is, what validation techniques do you use to validate your model predictions? And are there any statistical analysis that you use to generate from your model predictions for the significance of your results?
So yeah, for the validation of our model, typically what the main study that we did was the one in Yemen, where we looked at the county level data sets from 2017 to 2019. We have the weekly number of cholera cases there. And what we did was we ran the model for all 3 of those years that we had the cholera case data. And we compared the model outputs with the case data. And if our model was like the threshold low, medium, high, fell into, a certain number of cases for the county of which the risk reflected, it would be considered like a success for that county. And basically what we did is we evaluated the model based on like typical model performance statistics. So accuracy, sensitivity, precision, F1 score, area under the curve score, all of those to kind of assess how good the model performed. And I believe that in the presentation, the citation for that paper is given. So you should be able to access that and read it if you're more interested about the detailed methods, but it should all be in there.
Thank you. Question 11. What are the best practices to transfer these models to other regions?
So the nice thing about our model is that we generally just are able to run it for any region that we are interested in. As I said, we might have to calibrate the model a little bit in terms of like the thresholds we're using for low, medium, and high. But the underlying principle of how cholera behaves in the environment is ubiquitous. It applies to cholera in all regions of the globe. And so we're able to run this model for anywhere that we're interested. So we've done it for regions of Haiti, to regions of Africa, to regions in Asia, as well as in Europe, such as in Ukraine. So thankfully, it's very transferable. However, transferring it to other diseases might be more complicated, as that would depend a lot more on the environmental conditions that promote those pathogens. But as far as just for cholera, we're able to run it for any region of the world, thankfully.
Great. Thank you, Bailey. So we want to thank our speakers for today, Dr. Jutla and Bailey Majors. And we had such wonderful information about model development and risk assessment or prediction for cholera. We thank you all for attending today's session. And we hope to see you in our future ARSET webinars. You can find out more about upcoming trainings from ARSET website, or you can join ARSET listserv to stay updated with upcoming trainings. Also, homework is due on 10th of April. It's posted on our website. And also, just a reminder that you will receive a survey from ARSET. Please provide your feedback. It's important to us. It helps us to assess our own training and what improvements are needed, or what topics are more relevant for your studies, what are the barriers. So you can provide your feedback through survey. So please, when you receive an email with survey link, we request that you complete the survey. That helps us a lot. And thank you all for attending this training, and we'll see you soon at the next training. Also want to thank our ARSET team for helping in coordinating this webinar. So thanks everyone. And thank you very much.